Okay, we are now recording and we can start the reading group session. So thank you all for joining, and thank you, Fabio, for your speech, your talk that you're gonna have today, and for accepting to do that. For this reading group session, we will be talking about modeling the background for incremental learning in semantic segmentation. The main speaker of today is Fabio Cermelli. And Fabio, I see that you're already presenting, so you're already set up to start your talk.
So thank you, first of all, to you that gave me this opportunity. So as you say, today I will present this paper, which has been presented at CPR, and it's a joint work with Massimiliano Mancini, which is here today, Samuel Rotabulo, which is working from Mapillary, Elisa Ricci, which is from University of Trento, and Barbara Caputo, which is my supervisor at the Politecnico di Torino. So this work, this presentation, I will present you first the incremental learning problem in semantic segmentation. Then I will introduce our method, which is modeling the background. And then I will show you the experimental setting and the result and a few conclusions. So let's start from the introduction. What is semantic segmentation? I think that all of you already knows it, but the goal is to assign to every pixel of an image a class label. So for example, in this image, we have three objects of interest, which are bike, car, and person. And we want to label each pixel of that objects as the corresponding class. And as you see, there are other pixels that falls in the background class. So all the pixels that does not belong to any of the class of interest are considered background. So what does it mean to make incremental learning in semantic segmentation? Let me start with this example. We want to train an intelligent car to segment cars and persons. So in the common machine learning setup, we have a huge dataset, which is labeled on car and person, and we feed them to the intelligent system that is able then to recognize car and persons. But if we have an image like this in input, well, it is able only to recognize car and person, and bike is considered as background. And what if we want to include also the bike class in this setup? Well, if we want to extend the knowledge of the model going from car and person to bike, we have three options. The first one is to relabel the huge training set, dataset, sorry, and it is very expensive, it's time inefficient, and also the original dataset may be unavailable. So if we get this dataset, we are discarding also the old model, and we are learning a new one from scratch. So we want to avoid this solution, and another solution is this one, where we have a new dataset with the new class of interest, but we are labeling all the classes known. So for example, if we want to learn the bike, but we know hundreds of classes, we will label the new class and all the hundreds classes that we already know, which is still expensive because labeling one image in semantic segmentation is very expensive and time consuming. So also we want to avoid this solution to introduce the new one, which is labeling only the new classes and consider all other pixels as background. Relying, of course, on the knowledge that we already have. This is cheap, this is fast, and it reduces all knowledge. So it satisfies all the constraints that we have in incremental learning. So let's state the problem in this way. Incremental learning is the problem of updating the knowledge of the model when new classes are discovered. And we want to do this in semantic segmentation by focusing only on the specific class that we want to train in the incremental step, while all the other pixels are considered background. So in the example on the right, you see that in the first training step, we are training for the person class, but we have already but we have also other objects such as car and bike in the image, but it is of course as background because we don't know what car and bike does mean. So when we are learning the car class, we only see the car class labeled, and all the other classes are seen as background, both the known one, which is person, and the unknown one, which is the bike. And then when we learn the bike, of course, we see the other classes as background and the bike class as in the ground. As you probably have guessed, there is a huge problem in this step, which is the background shift, because in every training step, the background semantic changes, including all the classes which are not loaded in the current training step. And so it may include objects that have been seen in previous learning steps or classes that will appear in future learning steps. So in this example, again, you see that in the first step, we are learning person and we have bike and car in the background. Then we're learning car and we have bike and person. Bike will appear in the future, and person we have already appeared, but now it is background. So how can we devise an incremental strategy to deal with this problem? So our motivation was to deal first with the background shift. So we start from a very common starting point for an incremental learning approach, which is the distillation, firstly proposed by Fee and Doyen for the classification task. And this distillation term basically says that you want to constrain the output of the network to be similar to the output of the network at the previous training step. However, this introduces two problems. And let me show you those problems with an example. So we are always considering the example of before. So we have this image and we want to include the bike car in a model which already know car and person. And let us focus on the red pixel, which is indicating a pixel of the person car class. So what will happen? The model will predict likely this pixel as pixel of the person class, because it knows that this is a pixel of the person car because it has seen the person car class in the past. However, if we train the model with the common cross-entropy loss, we incur in a problem because the ground truth for that pixel is the background. And so we are pushing up the background probability and we are pushing down the probability of the person's class. So what we can do, we can sum up the probability of all the old classes and the background and compare them with the background class. In this way, we are saying to the model that we don't know if that pixel is a pixel of the background, the real background, or is a pixel of an old class. And so we sum up the probabilities of those classes. And when we have this new probability distribution, we can compare it with the cross-entropy loss and minimize this new cross-entropy loss based on these unbiased, let's say, probabilities. So this is the first contribution we have made. We devised these modified cross-entropy loss, where we are modeling the fact that classes that we already know are now present in the training step, but as background. The second problem is related to pixels of new classes. So the same example of before, but let us now focus on the bike pixel. Of course, we are training this with the common cross-entropy loss, since if you look at the first cross-entropy loss, the revised cross-entropy loss, the loss for new classes is the common cross-entropy loss. But what can we do with the distillation loss for a pixel of a new class? So first, let's see the model predictions. For the new model, it is very likely that the model will predict the pixel as a bike, and the background probability is very low. But the old model does know nothing about bikes, and so the probability will be high for the background and low for other classes. And so if we use the common distillation loss, we will push up the probability of the background and also giving the model two different signals. In the cross-entropy loss, we are pushing down the bike probability, and in the distillation loss, we are pushing up the background probability, giving an unstable training. So here, again, what can we do to model this? Simple. We can sum up the probability of the background with the probability of the new classes. And in this way, we can then obtain a new probability distribution where the probability of the old classes is kept unchanging, but the probability of the background is the sum of the real background plus all the probabilities of the new classes. And in this way, we can use the common distillation loss among the new probability distribution and the old one. And as you can see, this gives a very stable training, and also we are able to mimic the old probability distribution for the old classes. So with this loss, what we are modeling? We are modeling the fact that the spectrum might have contained in previous learning steps classes that now are background. Classes that in previous learning step are seen as background, and now we are seeing them as ground truth. So we are learning them. And this is very effective. And as you can see, it's very also simple to compute them. The third contribution we have made is the initialization of the new classifiers. So when we have to learn new classes, we have to initialize the classifiers. The first simple solution can be initialize them as random, but we made an assumption. We assume that the new classes will be likely predicted as background by the old model. And so we decided to spread the probability of the background class equally to the background and to the new classes. And this is very simple because we can just modify the bias of the old background in the new one. And for the new classes, we can just copy the weights and subtracting the log of the number of classes to the bias. So if you see this formula, it's very simple. And if you compute the math, it will be back to this one, which states that the probability of the background class will be spread among the new classes and the new background class. So summing up, we propose to revisit the cross-entropy loss and the distillation loss to model the fact that now we have classes, the background shift. So classes that previously appeared as background now are currently learned, and the class that we already know now appear as background. And moreover, we propose the novel initialization scheme for the new classifier to keep the training stable. So we validated our approach on two different datasets. The first one is Pascal-VOC, which is a very common dataset that includes 20 object classes from a very different context, but it does not include staffed classes, for example, sky, grass, road, and so on. So object classes are something which is countable, while staffs are not countable. And these datasets provide only countable classes. We proposed 3 different settings. We tested on the 19 classes, then 1, 15 classes, then 5, 15 classes, then 5, sequentially, one by one. And we also proposed 2 different data setups. For the first one, we took inspiration from the paper of Umberto, which I saw before, which is the disjoint setup, where each image appears only once in the training. So basically, the dataset is made in this way. For the base training set, we exclude all the images that contains at least 1 pixel of a class that is not in the current training set. And in this way, of course, we have that images appears only 1, and but there is a drawback, which is that in every step, we don't see pixels of future steps or classes that will appear in the future. And this is not so realistic, since in the real world, if we have a big label dataset, probably we have also pixels for classes that we are not considering right now. So we propose the second setup, which is the overlapped, which is inspired by works in incremental object detection, where images can appear multiple times, but with different labels. So if an image appears in the first training step, it can appear also in the second training step, but only with the classes which are considered in that training step. So if in the first step we have, for example, person, and we have the image at the top left, we see it only labeled with the person and not with the motorbike. So the motorbike bike is considered as background. And in the following training step, if you are training the motorbike, we see the same image, but only with the label of the motorbike, and the background is considered as background. The second dataset we considered is AID20K, which is a huge dataset which contains 150 classes from very different contexts. And this dataset, different from Pascal, contains both objects and stuffs. So there is things like sky, grass, and so on. We also here propose 3 settings. The first one is 100 classes, then 50. The second is 100 classes, then 50, but sequentially 10 by 10. So we have 5 incremental steps. And the third one is 15 classes, then 15 classes, then 15 classes, which made up of the first step, the base step, and then 2 incremental steps. To provide a fair comparison, we made the experiment on 2 different orders for the classes, and we report averaged results. I will go very brief on that. It's the architecture we used for training. It's the v3 architecture with a resident 101 backbone and an output slide of 16. We followed the same training protocol of the paper of v3, and the only thing we modified is that on the incremental step, we use a learning rate which is 1/10 of the original learning rate. So in the base learning step, we use a learning rate. In the following learning step, we use the same learning rate, but at 1/10, so divided by 10. Okay, so we also care a lot the fairness of the results. So we compared with many different baselines, and we decided to use mainly two families of approaches, which are the distillation approaches and the parameter regularization approaches. The distillation approaches are, as we saw before, learning without forgetting multi-class, which is basically the same, but using the binary concentric loss and not the common concentric loss. And the paper proposed by Umberto Micheli and Pietro Zanutic in ICCP workshop 2019, which is incremental learning techniques for semantic segmentation. The parameter regularization approaches are path integral, which is also known as synaptic intelligence, elastic way consolidation, and the Riemannian walls. Again, since we care a lot of fairness, we also search the best hyperparameters following the validation protocol proposed by Delange et al., which basically says that we first train the network with the lowest regularization possible. And then we increase the regularization strength up to the point when the performance on the new classes drops too much, where too much can be a percentage point. So we decided to use this protocol considering the mean accuracy on the novel classes, and the performance drops as 10%. So all the regularization strengths are validated in this way on all the methods. And since we have found that the methods are quite robust to this parameter, we decided to use the same parameter on all the settings and datasets. So this is the first result on Pascal-VOC. It's a huge table, but don't worry. I will go through it. The first family of approaches is the parameter-based regularization, and as you can see, they are quite bad, in the sense that they are close to the learning fine-tuning approach. They forget a lot of the previous classes, especially for the multi-step setting, which is the rightmost one. Then we have the distillation approaches, which outperforms all the previous approaches, especially the parameter regularization ones, especially on the all classes. However, on the multi-step, they still struggle. And so, as you can see, our method is able to perform good not only on the single step scenario, but also on the multi-step one. In this slide, I want to show you one very hard case for the Pascal-VOC dataset, which is when we train objects which are similar. So consider that in the first step, we are training bus and cow, and these are the results. So the output is smooth, it's good. But if in the second training step we are training for train and sheep, the model will be biased toward the new classes. And as you can see, the fine-tuning approach will label the bus as a train and the cow as a sheep. While our methods and the distillation approach proposed by Umberto is quite good in keeping the performances. So here I show you an ablation study which demonstrates that our method is all the contribution of our method are valuable. We started from on the Pascal-VOC dataset on the overlapped step. We started from the learning of forgetting baseline, and first we included the cross-entropy loss, showing that the results are better, especially for all classes. Then the distillation loss, and the performance increased both for new and old classes. And then we have the initialization approach, which improved especially on the novel classes. And this is due to the fact that it provides us smoother training for the new classes. Then I have also some results on the 8020K dataset. We did not consider the parameter regularization approach since we found that they were quite difficult to train in this setup and gave poor performances. So we started from the distillation approaches. And as you can see, they are good on the single step setup, but they are not so good in the multi-step setup. And our approach, as before, is good on both. So it's good only also on the multi-step and on the single step setup. Very interestingly, also on the single step setup, we are very close to the joint training, which is the golden baseline, where when we train the model on all the classes on a single step. So I also have some qualitative results. This is some images from the 820K dataset, and this is the output for our model and model of outer distillation approaches. So if you want, I will upload a slide so you can see all the qualitative results. Okay, let's jump to the conclusion. In the future, while we address the background shift issue, in the future, we want to address another problem, which is that when we are learning new classes which appear in similar contexts of the previous one, the performance drops. So, for example, in the case of before, when we are learning sheep after the cow, we have problems. And so, how to solve this issue? Well, we ideated two solutions. The first one is to have also rehearsal approaches that can be using exemplars or memory that store previous images, or a generative approach. And the second solution can be effectively use the old knowledge by pseudo-labeling all the images of the new class, of the new dataset, just to spot out all the old classes and make a correlation among the new classes and the old ones. So in conclusion, we studied the problem of incremental learning in semantic segmentation, identifying the background shift issue for the first time. We proposed a simple yet effective modification to the distillation approaches to tackle this scenario, and we benchmarked that approach with other several methods onto popular segmentation datasets. The code is online, it's on GitHub. If you want, you can try it. It's, of course, open source, and if you have any issue, you can drop me an email. I will be happy to hear you. So thank you.
Thank you so much, Fabio, for your great talk. Really enjoyed it. Maybe I have a few questions. So first of all, I have seen that let's say the most difficult scenario, you are essentially training over a sequence of, let's say, tasks or let's say batches. That it's 5 or 6, if I remember correctly, right? So 20 maybe classes, and then followed by 4 or 5 updates with just one class, correct?
Yeah, on Pascal-VOC.
Yeah, well, I don't remember. But well, this is the most difficult scenario, right? Of your setup.
Yes. The most difficult scenario is always the one with multi-steps.
Okay.
So for Pascal-VOC is the one when we train on 15 classes, then one by one the other 5. And on ADA20K, it's a scenario when we have, for example, 100 classes, then the other 15, 10 by 10, 50, 10 by 10. Or the one when we have only 2 training steps, 15 and 15 classes.
So you have always 6, let's say, incremental steps. Right. 5 incremental steps and 1 base, let's say, initial batch.
Yeah.
Okay, great. So did you try to see if your method can scale somehow to a longer sequence of tasks? And yeah, if you have some insight about that, because you know that's really important thing to understand if you can really use this technique maybe in an application, detection application, something like that, where of course if you have just a few incremental batches, you can still somehow permit yourself to retrain the whole system from scratch, right? What do you think about this?
Yeah, we didn't consider that setup. For example, using 10 classes by 10 classes in ADA20K will be very interesting. But of course, it will be very hard since somehow if we have a base training step with a lot of classes, we are able to learn good features for the model.
Yeah.
And then we can just improve it. And if we have to start with, for example, 10 classes with the high variability that there is in this setup, it will be hard, of course. For example, think about learning 10 classes, which can be road, sky, car, and other related.
Yeah.
And then learning what is a cow. It will be very hard without destroying the performance on the previous steps.
Yeah, maybe you can consider like pre-training, let's say, on Pascal-VOC and then using the other data set just as an incremental stream of data, or fusing different data sets for detection, so that you can create a longer sequence. No, that was interesting indeed. And
I agree.
Cool. So did you? I mean, in this work, you didn't consider using replay examples, right? I mean, if I understood correctly, you don't use that. That's cool. But did you consider using them to improve or have you tried using them to improve the final accuracy? What are your thoughts about that?
First of all, it's very expensive in semantic segmentation using exemplars, and that's the first thing that we thought. So storing, for example, images of Pascal-VOC, even if they are very simple, they are like 512 times to 512, so they are big. And also, we need also to store the labels for them, and then we need to include them in the same step. So it is very costly also because the training time.
Right.
And that's the first reason we avoided them. And the second thing that we thought is that we want to start from the most challenging setting. So we didn't consider exemplars to see if also we can exploit the pixels that are background in the training step, but may include classes of the previous training steps.
Yeah.
So I think that in semantic segmentation, in the image, there is a lot of variability. So you may consider not use exemplar for this reason, since maybe you have already the all classes in the images, but you don't see it labeled.
Yeah, that's interesting. An interesting consideration that you have like a natural rehearsal from the natural video stream that you, or maybe the images you're considering. Yeah. So that's anyone. Yeah. Please continue.
No, I mean maybe it's not so visible by the Pascal-VOC dataset, which contains only few images, where a few objects per image, but it's very visible in the AD20K dataset, where you have kind of 10, 15 objects per image. So in this case, you see better than this consideration in the image.
Yeah, totally. So does anyone have another question for Fabio?
Maybe I have one.
Please go ahead.
First of all, thanks for the great presentation and congrats on your paper. And maybe you, I heard you said that you removed all the classes in the background. The point is, if you're a human, when you go around in the streets, for example, there is no background. Like, you don't see any backgrounds. You can always tell what's the class for the background, right? And so in this case, like doing incremental learning on this case in which you have a background, it's kind of a constraint on a real, like, human level segmentation system, right? So how do you think this could be extended in a way that there's no need for a background? Like, I don't know if I explained it right, but
yeah, I understood, but it's hard to answer you. Instead, we focus on the realistic setup. So it will be nice to have a lot of classes, and so without having the background class. But in real use cases, it will be hard because your model cannot know all the objects that can be present in the real world. Something that we have considered is to have a general classes for the objects. So for example, instead of using only one background class, we may consider to use multiple, let's say, general classes. So you can have general animal and then the animal classes. You can have a general object. You can have general stuff and so on. And this is a setting where you may exclude the thinking on the background, but you still have manifold back classes, which are in some way multiple background classes.
okay. Yeah, I understand. And I mean, what I also was thinking is that maybe you can do some like unsupervised segmentation on the background, and then you will have some indication or something like that. But was just some guess.
Like
Thanks.
such as a pseudo-labeling approach, you mean?
Sorry?
Such as a pseudo-labeling approach,
Yeah,
do you mean,
something
or
like
something?
that. Or yeah, exactly.
Yeah, it's something that we are discussing right now with Massimiliano that I know you know.
Yes.
And it's something that we are discussing, but it's not so simple since in our method we are we are already doing something like this by summing up the probabilities. So this is a kind of pseudo-labeling approach, but of course we can do better. So we are working toward it.
Okay. Okay. Thanks for your reply. It was very interesting. Anyway, like, it was great.
Thank you.
By the way, I would like to say that Enrico is shy, but he has an ECCV work accepted on continual learning, and I would like to hear from you, maybe in one of the next seminars.
Oh, totally.
Yeah.
Totally.
Okay. Okay. Could be maybe. I mean, my work is not even on archive actually.
Okay.
So we need to do a last polish on the article, and then maybe I will do it.
Of course, whenever you're ready, just tell me, and we squeeze your presentation in a few.
Yes.
In the next, reading group sessions.
Yeah, I mean, I have already presented a paper here, not my paper, but
yeah, I remember. Cool. So, do we have any more questions? Guys, can you hear me?
Yes.
Okay, cool. I thought I was completely disconnected. But yeah, so thank you all for joining. I think it was a great talk about one of the first applications of continual learning semantic segmentation. So thank you again, Fabio, for your great talk, and all of you for joining. You will find the recording of this talk on YouTube on our ContinualAI channel. You can subscribe that channel to be always updated about future videos. And then I'm going to create also a forum topic about this talk in which you can continue asking questions to Fabio, and I ask Fabio to eventually upload his slides if he wants to this thread so that we can have a record, let's say, of this great talk. So thank you so much again, and I'll see you guys in the next reading group session.
Thank you very much. See you.
Thank you.
Bye. Thank you.
Thank you. Bye.
See ya, guys.